All right. So on Monday, I introduced how you actually analyze multivariate data and how do you actually look for patterns. And the main tool that we used for this was this principal component analysis to look at these patterns, or the EOF analysis. And today we want to spend the 2 lectures on how do you actually interpret what you see there. And you will see that this EOF analysis of principal components is a very famous tool in our field. But the interpretation of these things that you see there is not trivial. It's not straightforward. So this is what we want to deal today with. And we start with a simple, I wonder if this is all going well here. So we start with a question. So if you look at this pattern, so you see EOF number 2 here in the tropical Atlantic, and it's green and blue means negative values, and red and orange and yellow means positive values. So you see it's the EOF number 2 here has in the region A negative values and in region B positive values. And the questions for me to you is, what do you see here? What kind of statement would you make about this? When you look at this, what can you say about the interactions in this domain? So I give you 3 choices, and you have to think about which one of these you think is true. So the first one is A, anomalies in region A will have a negative correlation with those in region B. So you have here region B, when this is positive, there's a tendency in region A that the anomalies will be negative. That's the first statement that you can make about it. Second statement might be, in average, region B is warmer than region A. So you see here there's positive values here in region B, and there's negative values in region A. So on average, there will be more positive values in region B than in A. And then as part C, anomalies in region A will be mostly independent of those in region B. So what's going on here in region B is unrelated mostly to what's going on in region A, but it may have a weak positive correlation. So when there's positive anomalies here in B, there will be positive anomalies in A, but this will be a weak relationship. So now think about which of these 3 statements you think is true. And don't think about what I might think or what the community thinks. Just think about, honestly, what you think would be a true statement. And I give you a few minutes, and then everybody has to make a choice. The general view is A is correct, nobody goes for B, and C is unlikely. And let me say something about B. So the thing about EOFs is that the sign of the pattern doesn't matter, because it will always go up and down, up and down, up and down. It will be positive, negative. Whatever statement you make about the EOFs has to be true if you change the sign. If you change the sign of the complete field, it would be B negative and A positive. It would be exactly the same EOF pattern, because the sign doesn't matter. So this statement B I have heard many times from people, but it cannot be true, because you have to change the sign of the whole pattern, and it has to still be the same statement. But if you change the sign, then B would be negative. Right? So B can't be true. Can already rule this out, because whatever statements you make about this pattern, it has to be true if you change the sign of the pattern, because this is more or less irrelevant, because the time evolution will always be going up and down equally. It will be as many positives as many negatives. But let's look at this log. Now we do the real lecture. So we go get this done here. Okay, so that's the port. So that's the outline of what we do today. So in the first part, I would talk about the deterministic mode view. This is basically the view that the community has about EOFs. This is how everybody reads the EOFs, and it's one way of going at this. My personal view is that this is not a good way of looking at these things, but I will explain this to you. So we start with, can you see this? I give you some examples from the current literature, and these are very high-profile examples. These are the most outstanding discoveries in our community, more or less. Where's my mouse? Okay. Then I give you a little cautionary note on these. I explain to you what's the difficult part about it, and then I explain to you how you would actually read EOF modes, like this one that I just showed you, how you actually read those things, and asking the questions, what are the true teleconnections? And then I give you an alternative view, another way of looking at these things, which is just more like thinking about stochastic models, and that the climate variability is a continuum. And I will give you a null hypothesis of what you should expect, and then actually how you would compare EOF modes of different theories or different data sets, and then we come to the conclusion. Okay, let's start with the examples from the current literature. So principal component analysis or EOF analysis is very high profile in the literature. If you look at the most outstanding publications in the last 10, 20 years, these are actually principal component analysis. So I'll give you 4 examples. The first one is the Arctic oscillation. So you look at the northern hemispheric sea level pressure or geopotential height variability, and there's a famous paper which somewhat defines the Arctic oscillation or the angular mode, which is from Thomson and Wallace in 1989 and 98. And it's been cited since then 1,500 times. And I will explain to you what this means in a bit. Another famous pattern, which is in the tropical Atlantic and more in the ocean science community, which is what I did my PhD on. But I will explain this also a bit what it means. And then the other famous one is the Indian Ocean dipole from Saji et al. About 10 years ago, also cited 1,000 times and more. And then there's this relatively new one, El Niño Modoki, which is this EOF analysis from Ashok et al., which is just 2007, but it's already been highly cited. So what does these citations mean? So in terms of management and government and money, all that counts is citations. Right? You are a good scientist if you produce a paper that is highly cited. So there's these so-called essential science indicators that management people look at. So on average, a normal publication in our community would be cited, if it's 10 years old, 11 times. So it's cited once a year. That's the median, the 50% value. An outstanding, very good 1%, or 1 out of 100 publications might be cited 100 times in 10 years. And those that we talk about here are these very hot, groundbreaking papers that have been cited 500 times or more. So these are very unusual publications that happens 1 out of 10,000 studies is like this. So these principal components publications are very high profile publications. And now I explain to you what these 4 publications are about. So let's start with this angular mode or the northern hemispheric winter sea level pressure. So Thomson and Wallace made this pattern here very famous. And I think what most people read in this, that there's a connection between what's going on in the Atlantic and what's going on in the Pacific. So this pattern here is EOF number 1, it explains 80%. And it somewhat indicates, this is I think how many people read this, and from those 1,500 people that have cited it, at least 1,000 of them think that there's, oh, where's my mouse? That there's a relationship and there's high pressure in the Pacific, there will be high pressure in the Atlantic. So there's somewhat a connection between the Pacific sector and the Atlantic sector that goes over the Arctic variability pole. However, if you look at correlation, let's say you look at the correlation of what's going on in the Atlantic and you correlate it with the Northern Hemisphere, you don't see any correlation with the Pacific. And if you make a correlation between the Pacific and the Atlantic, you don't see a positive correlation. If anything, you see a negative correlation. So there's been a dispute with some people arguing that this, what Thomson and Wallace are saying or indicating that there's a connection between the Pacific and the Atlantic is not true. And community view is it is true, and then the minority view is it's not true. Similar story here about this pattern. So about 20 years ago, there were some people studying rainfall in northeast Brazil, in this region here. And they found when there's a drought, it is negative temperatures in the ocean here and positive temperatures in the ocean here. So it's very important for them to know what does this pattern do, what is the index like. It will determine whether there's a drought or whether there's lots of rainfall in northeast Brazil. And then other people picked this up and said there's a mode going on in the Pacific, in the Atlantic, that has SST anomalies that are positive here, then there will be SST anomalies negative here, and there's a connection between these 2 regions, suggesting some ocean dynamics causing this interaction with a negative correlation between the north subtropical Atlantic and the south subtropical Atlantic. And again, the same stories, some people don't believe this, including me, that if you make a correlation of this box here, and there's no correlation to the north. There's a little bit, if you can see it. Well, there's basically 0 correlation. And again, if you correlate the northern part with the southern part, there's 0 correlation. So again, you have this sophisticated principal component analysis that tells you there's a relationship. And then you take the simple method, and it says there's no relationship. Which one is true? That's complicated. The one that probably most here in Australia know about is the Indian Ocean dipole, which is the second EOF of the Indian Ocean monthly mean SST anomalies. So the first EOF is this big monopole here. And they argue the first EOF is El Nino, mostly. And then they argue that the second EOF is something which is something like El Nino in the Pacific, but it's an El Nino kind of dynamics in the Indian Ocean going on. And people are highly excited about it. But again, the story is, if you look at the correlation, this box here in the east has actually positive correlation with the west. And the box in the west has positive correlations with the east. So you, again, if you think simple and you do correlation analysis, you don't see this. So they argue that the EOF analysis can find a somewhat hidden structure in the data that you don't see with a simple analysis. And in a similar case, is the most recent case is the El Nino Modoki. So everybody knows there's El Nino, which is this pattern. But recently there's been the discussion there might be a second El Nino kind of variability, which is different dynamics from El Nino, but it's also in the tropical Pacific. And they call this El Nino Modoki. So and then it's an anomaly here in the Central Pacific and a somewhat negative anomaly to the east of it. And that's the EOF number 2 explains 10%. And again, if you make box correlation, I don't show you here, but I'll show it to you later, you don't see this anti-correlation. There's always positive correlations in this. So what is the common structure in these examples? So the first common structure is they identify one EOF mode, one pattern, and they say this is a physical mode. There's a physical relationship that we can explain this one pattern. That's the basic approach. They also just discuss the single EOF mode, not in context with the other modes. They basically have the idea you can take one mode and try to understand it, and there's one physical mechanism that explains this mode, and this is independent of what all the other EOF modes are doing. Right? So that's a few that they have. They discuss one mode independent of the others. And the interpretation that they take is that the structure that you see in this EOF mode is a coherent teleconnection. Like this dipole that I showed you at the beginning is, if it's positive on one side, then it's negative on the other side. It's a coherent interaction between these two things. And also what they see is that simple modes are unable to find this because they are not sophisticated enough. Right? They think that the EOF patterns can reveal underlying teleconnections that simple methods can't find. So you think you have a more sophisticated method. So basically the community view on EOF analysis is a very sophisticated, powerful technique. It can reveal underlying teleconnections that simple methods simply can't find. So you have something which is more powerful than a simple correlation analysis, and so on. And they equate a single mode with a physical explanation. And they think modes are independent, so they don't look at interactions. They take one mode, define it, like EOF1 in the Pacific is Enzo, and EOF2 is El Nino Modoki. So they have this view that each of these modes represent a different entity, a different mechanism, a different physical mode. And this is somewhat a deterministic view. Right? So they have somewhat the idea that climate variability can be described with deterministic coherent teleconnections. So you have one structure and that has a certain equation and that goes up and down. It's a very deterministic view on the climate variability. So I call this the deterministic mode view. So this is the first part of this lecture that we talk about this thing. Okay. So from this you get the impression that you have a very powerful technique that can actually find things that are not easily found with other simple methods. And it's interesting that the community has this point of view. If you look at textbooks about EOF analysis, you will see that they somewhat always give a warning to this approach. And I just cite here Storch and Sweers. So if you read Storch and Sweers, they have the statement here. While it is often possible to clearly associate the first EOF with a known physical process, this is much more difficult with the second or higher order EOF, because it is constrained to be orthogonal to the first EOF. So all these patterns have to be dissimilar. If the first one is a monopole, then the second one has to be somewhat a multipole. So, however, real-world processes do not need to be orthogonal patterns, and they don't even need to be uncorrelated indices. In fact, patterns that most efficiently represent the variance do not necessarily have anything to do with the underlying structure. So EOF modes might be very efficient in presenting the data with very few modes, but understanding the data is a totally different issue. Right? If you want to understand things, you don't necessarily need to have the most efficient presentation. So this is a kind of a statement that you often read from those people that write statistic books, but somehow seems to be ignored by those people that are applying it. So I give you a cautionary note. I give you an example that I constructed basically, and then you see how you actually, what the difficulties are in interpreting these patterns. So the question is, how can we find the underlying modes of variability with EOF analysis? So EOF analysis is a very powerful tool, but how do we actually find the underlying interesting structures? And I will give you a discussion of a well-defined constructed example, and this is based on a publication that I had about 10 years ago. And it came out of a dispute that I had with lots of people when I did my PhD. And eventually I submitted it to a journal because of the Saatchi Indian Ocean dipole paper. But it's a while ago. Okay, let's construct an example. So in order to understand my approach to statistics is always when I use a new tool, I try to understand it by setting up a simple example and see what the statistic tool does with it. So this is also how I try to understand EOF analysis. I build myself a simple example and see what the method is doing with it. So the example that I constructed here is somewhat what I think might be a null hypothesis. If you don't know anything about your data and you think there's a region to the left, there's region A, and then there's region B, which is to the right, and I wouldn't know what's going on, I would think maybe region A is doing something, and the other two regions, the one in the middle and the one to the right, doesn't care about it. Something is going on in region A, the one to the left, and it's unrelated to what's going on in the other ones. And I think in region B here, which is the right region, I think there's something going on as well, and it's unrelated to what's going on in the other regions. I think this is if I know nothing about region A and B, I would think they do something independently. But I also know climate is diffusive. There are some global impacts on climate. I think there might be something that connects everything. There's diffusive system. If you wait long enough, there might be an influence. So the way I set it up is I think you think there might be two independent things going on, and then there might be something connecting it, something which is weak. So I set up an example here which says the first mode is only in the left point and explains about 44% of the data, so roughly half of the data. And I think there's another one to the right which is slightly less, but also 36% or 35% of the data is explained with that. And then there's a weaker mode, but still relevant, which explains 21% of the variability. And I think this is something which is a reasonable idea to start with, and it has some meaning for most of the data that you look at. You can somewhat think in these kind of terms. Of course, it's somewhat motivated by the literature examples also. What you can notice here is that the way that I set it up, if you think about orthogonal patterns, then you think this pattern here, if you project it onto this pattern, the correlation between these two patterns would be 0. But then if you correlate this pattern with this pattern, they will project onto each other. They are not orthogonal. So the way I set it up, the patterns are not orthogonal. That is probably one of the points, also what Storch and Spear mentioned, is that those things that are physically relevant not necessarily are orthogonal. So I set something up which is not orthogonal patterns. To describe this mathematically, you put this into a matrix. So you have your pi matrix of patterns. These are the same pi that I mentioned on Monday. And you put the first pattern in the first column, the second pattern in the second column, and the third pattern in the third column. So the first pattern is 5, 0, 0. You have the 5, 0, 0 here. Second pattern is 0, 0, 4.5. You put this in the second column. And the third pattern you put in the last column. And then I made the assumption that the time series evolution of each of these patterns is independent. So I assume they are uncorrelated. Whatever goes on with this pattern is uncorrelated what goes on with this pattern, and same with the other global pattern. So when I set it up like this, I can use the linear algebra and actually calculate my covariance matrix very easily. So the variance of a mode would then be, and the variance of any of these modes is just these patterns multiplied with itself. Because I defined these time series to just be uncorrelated and have no units, just standard deviation 1 as time series. So the time series are normalized, and I can just define the variance as being the pattern vectors multiplied with observed, so this is a vector product. Then the covariance matrix is just this pattern matrix multiplied with the pattern matrix itself. So again, the covariance matrix was on the diagonal. We had the variance at each point. So let's start with the first point. This is the left point here. The variance at this point is the variance of this pattern plus the variance of this pattern here, which is 0. It's nothing. So 5 squared is 25 plus 0 is 25 plus this pattern, which is 4, is 29. So the first variance at the first point is 29. The second point is the point in the middle. This one does nothing, is 0. This one is also 0. And this one here is 4. Is 2 times squared is 4. So the variance in the middle is 4. And then the last point is the right point, is 0 plus 4.5 squared, which is 22.25. So 20.25. And then the last one here also has some variance there. It's 4. So get 24.25. So the diagonal elements are just the variances, and I can just get them from the patterns. That's the way I constructed it. And then the other ones here, this one, and this one, and then symmetric on the other side. These are the covariants. So how do the points covary with each other? So the only way that this point covaries with this point, there's nothing that makes covariability from the first mode because it's 0 here. The second mode is 0 in both. This also gives no covariance. And the third mode has a connection between the left point and the center point. So the only mode that gives you a covariance between the central point and the left point is the third mode. So the third mode gives you 2 multiplied by 2, and that is 4. And that is how you get to this point. And the same for the other two. The only connections that exist between these points in the middle and to the left, and the middle and the right, and all other combinations is only the third mode. The other modes give you no connections. They are just local modes, either on the left or on the right, and nothing in the center. So the only covariance that I get is covariance from the third mode. So it's always 4. So I have a well-defined covariance matrix, and if I know the covariance matrix, I can compute my principal components by doing the eigenvalue problem. And I can create myself a data matrix if I want to. I would just project the time series matrix multiplied by the pattern matrix. I get my data matrix if I would like to have a data matrix. But it's not relevant for this discussion. Okay, so these are the physical modes that I set up, and let's see how the EOFs look like. So first of all, I can do regressions. I can ask the questions, how does this point would correlate or regress to the other points? And I can just do it by algebra. There would be a correlation between the left and the others because of the first mode here, the third mode here. There would be a positive correlation between all points and the right point, and there would be a positive correlation between the central point and all the other points, just from the regressions or correlations. And the EOFs would look like this. The first mode would be more or less a monopole, explaining about 56% of the data. The second mode would be a dipole, centered in the left and the right, explaining about 40% of the data. And then it would be a small EOF, which is a positive, negative, positive, a tripole kind of structure, explaining about 5% of the data. And let's look at this a little bit in more detail. What does this mean? So you have this, we set up a system with these physical modes. By construction, they are our physical modes. And we look at the EOFs, and we see this hierarchy of multipoles. Monopole, dipole, tripole. And so the first thing that you probably the thing that you can then calculate is also the time series. Since I know how I construct my data, I can estimate that the time series of Pt1 would be related to each of the time series of the modes. And this is the amount of variance that each of them contributes. So this one, first mode goes with 0.7, second mode goes with 0.4, and third mode goes with 0.5 to create Pc1. So Pc1 is a linear combination of the PCs of each of these modes with the amplitudes just shown in this table. And then the same you can do with PC2, and the same you can do with PC3. This is all just linear algebra. There's no uncertainties in this, there's no sampling uncertainties. This is just exact numbers from linear algebra. So first thing that you notice is the EOFs do not look like my physical modes. Right? So first of all, I have here an EOF number 1. That looks a little bit like mode number 3, but mode number 3 had only 21% variance. This one has 56, so more than twice as much. And then EOF2 is a dipole, so negative here and positive here, suggesting a negative correlation. but there is no negative correlation of any kind in this, the way I set it up. Right? So this pattern is very different from what you put in. And what you also notice is an oversimplification. If you add up EOF number 1 and EOF number 2, they explain 95% of the data. So you would argue there's 2 modes going on and nothing else, because 95% of the data is the 2 modes. But this is not how I set it up. I mean, I set it up with 3 modes, and the third mode explains 21%. So the EOFs are oversimplifying things, but they make things sum of into 2 modes, where actually there should be 3 modes, and this is what you don't see in the EOFs. The third mode is much weaker and has a totally different structure from what we would think about the third mode. Each of these modes, EOF1, EOF1, EOF2, and EOF3, is a superposition of all modes. So PC1 is a superposition of all 3 modes, PC2 is a superposition of all 3 modes, PC3 is a superposition of all 3 modes. So basically they have messed it all up. Right? Each of these modes is including all 3 physical processes. And then of course you have this dipole syndrome, so another one now. About the superposition, what is interesting is this part 3 here. It says what's going on in the center is anti-related to what's going on to the left and to the right. Now look, the way we have set it up, what's going on in the center, mode number 1 does nothing in the center. Right? And mode number 2 also does nothing in the center. It's only mode number 3. So the only relationship that with the center and the other 2 regions, to the left and to the right, exists as a positive relationship. But this here suggests there's a negative anti-relationship. So this mode number 3 is highly artificial. Right? And if you look at the time series evolution of mode number 3, that X in the center here, it has mode number 1 in it, which has no influence on the center at all, 0. And it has mode number 2 in it, which also has 0 influence on the center. So somewhat this PC3 is a highly artificial construct that has relating a center point, a center of your domain with the other regions in a totally artificial way. But nevertheless, of course, it's a mathematical deconstruct of our data. It presents our data completely, but it's, from a physical point of view, highly artificial. So let's compare again this community view and now knowing this cautionary node. So the community view was that we have a sophisticated, powerful technique. I guess my cautionary note would be that EOF analysis is often misunderstood. They're reading something into this data which is not there. And they think, community thinks that EOF analysis can reveal underlying teleconnections that simple methods cannot find. I think EOF analysis produces teleconnections that do not exist. They are not, there's no underlying physics for this. And they take a single EOF mode and they think it's a single physical process. But as a matter of fact, a single EOF mode is a superposition of everything that is going on, of many physical modes. And maybe slightly reformulating this in the second part, I will reformulate this a little bit with a so-called stochastic continuum. And I explain this then later a little bit. They think modes are independent of each other, which is not true. You have seen in the previous example that each of the EOF modes is a combination of 3 different things. So you can't really say that an EOF mode would be independent of other processes. They're really all related to each other. You can't discuss them independently. So it's much more likely that they depend on each other. You have to discuss the EOFs as a whole set and not individually. And so they have this deterministic view when they think that there's coherent teleconnections. That is very much possible, but it becomes very complex if there's more than one thing going on. If there's a combination of 3 or 2 or 3 or 4 patterns going on, it becomes very complicated. Although it seems simple, 3 seems to be a small number compared to the dimension of the climate system, which would be 10,000s or millions. But I think 3 is already very complicated. So be very careful if you look at these patterns. So that was first of all a cautionary note. Obviously the community doesn't like this. So when I publish this in the first week I get a comment. And the comment basically says that I'm stupid. So DL stands for Dommenget and Latif. Latif has been my supervisor as my PhD. Questions the existence of the Indian Ocean dipole. That is true. I do question the existing of the Indian Ocean dipole, at least from the point of view that the way that they presented it and arguing with the EOFs, I would say that this is not true what they are saying. They argued, the argument put forward by Dommenget and Latif, however, suffers from misinterpretation of statistical analysis as well as misuse of statistical techniques. So they think I'm stupid, I don't know what I'm doing. This is difficult to agree on. So they had this communication. I have to, of course, reply to this because I can't let this stand in the literature without saying something about it. And I'm really unhappy with this because it's now published and the editors and the referees says it's wrong what they are doing. But it's okay to publish it because my reply stands next to it. But if you look at the citations, people cite the comments as evidence for the Indian Ocean dipole. But the comment is plain wrong. And that is, I don't agree with the editor on this, that they should publish it. Because I think if something is wrong, you cannot publish it. And I think from the algebra that they are using, everybody agrees that this is wrong. I'm showing you what they are doing. So here's their comment and my reply to it. And I just show you my reply, but I'm showing you what their comment is. So their hypothesis is there's ENSO, which is EOF number 1. Can you read this? Okay, there's ENSO. And then there's an Indian Ocean dipole, which is a new dynamic existing in the Indian Ocean. And I say, okay, that's probably not true. I think there's EOF number 1, which is related to ENSO, and then there's something going on in the left of the Pacific Indian Ocean and the right of the Indian Ocean. But if you look at having these two hypotheses and you look at the statistical data, they are identical. Right? If you have these two hypotheses, these are my hypotheses that there's no Indian Ocean dipole and ENSO, or their hypothesis is that there is an Indian Ocean dipole and ENSO, the statistics would look exactly the same. You can't distinguish it just from just looking at these statistics. Both hypotheses are true. So you have to do something else in order to understand it. So just arguing with the EOFs like Saatchi is doing in the Nature paper, I think you can't say which one is true. You just would say they are both consistent. Both hypotheses are possible. So what you really have to do is you have to find a way to get rid of ENSO. If you have to find a way that you can remove ENSO out of the Indian Ocean, then if my hypothesis is true, you would see that the left part of the Indian Ocean would be uncorrelated to the right, and the right part would be uncorrelated to the left. And if the hypothesis of the dipole is true, then you would see the Indian Ocean dipole as EOF number 1. So then things would be different if you could remove ENSO. But how do you actually remove ENSO? And I think this is where everybody who knows something about algebra know it's wrong what they are doing. But they say they take out EOF number 1 because they say EOF number 1 is ENSO, which is not true. A part of EOF number 1 is ENSO, but maybe 50% of it is ENSO, maybe 60%, but it's not ENSO. So I'm saying you can't assume that EOF 1 is ENSO. This is just basically what they do is they're trying to prove their statement with that they have made an assumption, and they do this assumption again to prove it, that this is wrong, right, and you can't do it. It's just a wrong mathematical way of approaching this. By construction, if you take out EOF number 1, EOF number 2 automatically becomes EOF number 1. This is just pure math. There's no way that it can be different. If you take out EOF number 1 by construction, EOF number 2 becomes EOF number 1. And they actually prove that they don't understand it by making statistical tests whether this is true or not. Because you don't have to statistically test it, there's a mathematical proof for this. Right? I was trying to argue that this is shouldn't publish this, but they say since I'm explaining it, it can be published. So you can't equate EOF number 1 with ENSO. It's just not working. So their assumption is that PC1 basically is ENSO, so it's, and generally it is ENSO. While I'm saying PC1 is highly related to ENSO, so 0.8 correlation maybe. But then there would be other things going into this PC number 1. So it can't be solved from this. This is how the comments stand. But if you look at some publications, here's one which actually tries to get rid of ENSO. So they look at the observations and remove ENSO by making a regression onto this region here. And then they take all the data that is correlated to NINU 3 out. And then they make a correlation of the left part of the Indian Ocean with the rest of the world. You see it's positively correlated. And the right side of the Indian Ocean correlated, it's also 0 or positive. So there's no dipole there. And then I do the simulations as well. They suppress variability in the Pacific and look at what's going on in the Indian Ocean. Again, there's no dipole there. So as it stands, we disagree on this, but most people believe the comment is correct. Although I think they haven't really looked at the algebra. But nevertheless, this is a kind of a dispute that exists in the climate community. So how do you actually read EOFs correctly? So I've shown you now that there's a way that people read these EOFs. They take a simple single pattern and I think they find a dipole and they think there's an anticorrelation. And that can be true, but it can be wrong. And how do you know that this teleconnection is actually a coherent teleconnection? How can you be sure about this? So far I just told you that it's difficult, and now I would like to tell you maybe how you could do it if you look at these things. So look again at these examples here. So here they argue that the Pacific is correlated to the Atlantic, and if you do a simple box correlation, you see that tells you a different story. There's no relationship between these two. So somewhat there's a probably this teleconnection is incorrect. What I'm suggesting, right? There's probably no strong. I mean, it says 80% of the variability is explained by this pattern. So some people interpret this that 80% of the variance going on here is related to what's going on here. 80% is a lot. I mean, it means it's a correlation of 0.5 would be 80% explained variance. But there's basically zero correlation. The same with all the other examples. They always have a pattern here which suggests anti-correlation, and you don't see that with a simple method. Right? So it's always, in all examples, here's the Modoki saying negative, positive, but actually it's always positive correlated. So how do you know if such a pattern that any of these patterns, how do you know that this pattern is somewhat true or real? I mean, it's difficult to say what real means because they are, of course, based on the data, so they are real in a sense, but how do you know that they represent coherent teleconnections? And I think the best way to understand is to start with a real example, a real teleconnection. And I think one of the most famous ones, which probably also introduced this EOF analysis, is the North Atlantic Oscillation, which has been known before people have used principal component analysis. But it's a pressure system in the North Atlantic that is, when it's high pressure here in the Azores and the subtropics, then there tends to be stronger low pressure over the Iceland. So there's a strong relationship between what's going on in the Iceland and in the Azores, and it controls more or less the winter weather in Europe and a little bit in North America. And if you make a correlation of this region here with the rest, you see it is indeed a negative correlation. So indeed, somewhat this relationship is true. I would say it's a true relationship, a true anti-correlation, a true dipole, true teleconnection, a true coherent interaction going on between these two poles. So the things that what really stands out, what you can look at, is the explained variance of this pattern. What you will notice is that the explained variance of this pattern here in this point, around Iceland, is larger than 50%. It's 60 to 70% explained variance. At the other pole, it also explains more than 50% of variance. So I think a key thing that you have to look for, if you think a teleconnection between region A and B is true, then that teleconnection should explain more than 50% of the variance. Then you can be sure it is a teleconnection. If it's not, you are not sure. It might be, it might not be, but you can be relatively sure if it explains more than 50% of the variance. The second thing is, if you look at the other modes, you have EOF number 1 here, explains 30% of the variance. The second mode is EOF number 2, explains 70%. It already is much weaker. It's just half as big. And it actually is in a region C, which is different from region A and B. So it doesn't explain much variance at the same regions. It is at a different location. So my rule of thumb for you, if you want to read the teleconnections and you want to make sure that they are real, the pattern has to explain more than 50% of variance at those locations, region A and B. Then you can be sure that this is a real teleconnection. And there has to be no other mode that suggests the opposite. There has to be no second or third mode or any other mode that in the same regions A and B, explain similar amount of variance and tells you the opposite teleconnection. Why is it? So why do we need to have more than 50% explained variance, and why does no other mode has to explain something there? I think we can go back to our simple model, example that we discussed on Monday. If you have a two-dimensional thing, and in principle it's a two-dimensional thing, we have a region A and we have a region B. In our simple example, it was Iceland and Azores. So region A is on the x-axis. So x-axis would mean something is going on over Iceland. It's just region Iceland. And then we have the region direction B. That is something going on over the Azores. So we basically have a two-dimensional problem. And if you look at this scatter plot, everybody that looks at the scatter plot would say there's an anti-correlation going on, right? You would easily see that there's an anti-correlation going on. Nobody would come up with the idea that there's a positive correlation. Right? It doesn't look like this at all. It looks like a noisy data which has some anti-correlation. So EOF number 1 actually gives you this anti-correlation. It's this dipole pattern. In that case, it explains 86% of the variance in our two-dimensional problem. And the second pattern has to be orthogonal. It has to be a monopole. Right? And explains much less variance. If you think that this scatter plot would be just a cloud, just an equally distributed cloud of points, then there would be EOF number 1 and EOF number 2 having the same amount of variance, 50-50. So in order to have the cloud to have a direction, there has to be a mode that explains more than 50% of the variance. And the other one would then have much less variance. So in the dipole case, that means our cloud basically has this anti-correlation. And if you have a monopole teleconnections, we would have the cloud forming a positive correlation. And in the dipole case, you would have a dominant dipole explaining more variance than any other mode. And if it's a monopole case, then the monopole would explain much more variance than any other mode. You can simply get this from this two-dimensional view. You have a cloud of points, and if they point to one direction, then this is the dominant direction. It has to be explaining more than 50% of the variance. So this is basically how we get to this. So if you think we want to make sure that a clear connection is true, it has to explain more than 50% of the variance. If it explains less than 50% of the variance, the connection might still be true in a sense. There might be a physical mechanism behind it, but you just wouldn't know from the data that you look at. You have to do more than just the EOF analysis to know whether there's something going on. And it has to be the one mode that explains most of the variance in this domain. So this explains 30% and the other one 17. You have to be clearly dominant. There has to be no other mode that explains similar amount of variance. Okay, let's look at our examples again. So I start with the simple ones, the topic Atlantic. It was EOF2 explaining 40% of the data. EOF1 explains more variance in the same regions. Right? They are the same regions where it has amplitudes which are larger than the dipole. That already tells you that EOF2 is not the dominant one. The dominant one is a monopole. The explained variance of EOF2 is shown here. You probably can't read the number. This is 40 and this is 50. So this explains around 40% of the variance, and this explains also around 40 to 50%. So it's not more than 50%, and that is why it's not dominant. You can't be sure whether this teleconnection exists or not. Probably, if you look at these clouds, you see something like this, you would suggest there's a monopole, but you wouldn't suggest there's an anticorrelation. So I think there's no indication that there's an anticorrelation here. The other example, Indian Ocean dipole, so it explains only 12% of the data, while the first EOF explains 30% of the data. It has much larger amplitude in the same regions that the Indian Ocean dipole has an amplitude. And if you look at the explained variance, it has actually almost no explained variance in the west. It only explains variance in the east and here to the south. And then, of course, the correlation is positive. So this is a clear case where you have the points looking like this case here. There's a clear positive correlation, and you have to have an orthogonal pattern, but there's no indication of negative relationships. It's this case here. I can skip this one. Of course, the Arctic oscillation, or the angular mode from Thomson and Wallace, is a bit more sophisticated, because this is EOF number 1, explaining 80%, and then you have EOF number 2, 14%, similar amount of variance, a little bit less, but you think, if you look at EOF number 2, it says positive in the Pacific and negative in the Atlantic, with a similar amount of amplitude than this one, but this one here is slightly stronger. So they are somewhat compensating each other. And if you look at the explained variances, they are hard to read, but this is 30 and 40%, so this explains 30% here and 30% there. So it's not that dominant, but still it's EOF number 1, and you would think it has some relevance. It's not completely zero, so there might be some kind of a connection, but it's probably very weak. Maybe I come back to this later in the second part of the lecture. So that was the deterministic mode view. And now in the second part, we look at this again at a different way and in the more stochastic continuum view. But we make a 10 minutes break and then we continue. Okay.